a Portland Community College Mathematics telecourse. A course in Arithmetic Review, produced at Portland Community College. Let's begin this lesson with a new vocabulary. Like fractions are fractions which have the same denominator, or stated more technically, fractions which have common denominators. This lesson will be a very blunt, short, easy one, but a necessary one to build into something that's not quite so easy. And it centers around this question: how do you add fractions? Specifically, if their denominators are the same, or they are like fractions. If they have like denominators, as it turns out, you do nothing to the denominator. It simply stays the same. Then to get the numerator of the answer, you add the numerators of these like fractions. So that's 10 plus 11 is 21. And then if it's reducible, reduce it. In this case, 7 goes into 21 3 times. 7 goes into 35 5 times. So the sum of these four fractions is 3/5. Very easy, isn't it? But the key idea is that the denominators had to be the same. If that were the case, do nothing to it. That's the denominator of the answer. Then simply add the tops to get the numerator of the answer, reduce, and you're done. Now see, when we multiplied and divided fractions, we work with both the tops and the bottoms. But with addition, no. They stay the same. Let's focus on that statement. To add like fractions, simply add the numerators. Write the sum over the common denominator and reduce if possible. Sometimes we'll ask you to leave it that form, but generally we want you to reduce it. An example. So you read this statement in the business magazine. The stock of the 3J's Corporation rose 1/8 of a point on Monday, 7/8 on Tuesday, 0 on Wednesday, 1/8 on Thursday, and 3/8 on Friday. What was the total increase for the week? The key word here is total, which means I want all of these fractional increases in stock value added. That is, what is this sum? Now the first thing we do when we're adding fractions, and as it will turn out subtracting, check to see that the denominators are the same. And they all are, except for the 0, but we recall that 0 divided by any number, specifically 8, is still 0. So if the denominators are indeed the same, we call these like fractions, and the denominator stays the same for the answer. Now all we do is add the numerators. So it's 1, 8, 9, and 3 is 12. Then reduce. 4 goes into the numerator 3 times. 4 goes into the denominator twice. And then you can leave it in this form, or, if desired, change it into a mixed number. So we can say the total stock point increase for the 3J company was 1.5 points for the week. That's it. When adding like fractions, keep the denominator the same and simply add the tops for the new top, reduce, then change to a mixed number if that's what's desired. The next lesson, on the other hand, will study how to add fractions where the denominators are not alike. And in order to do this, we will have to recall a lot of specific new skills taught in the last chapter that we've been reviewing for the last 3 or 4 lessons. So let's do one final review before we get a problem like this on that topic, which is finding the least common multiple of a series of 2 or more numbers. Now these are fairly small and simple numbers, which we want to look at just to focus in on what we really mean once and for all by the phrase least common multiple. We're asking what is the lowest single number that each of these numbers will divide into. Now some students in the beginning want to find the lowest number that will divide into these, which of course would be 1. But what we want is the lowest number that each of those 4 numbers will divide into. So we can see that 14 is the lowest number that the largest one, 14, will go into, so it'd have to be at least as large as 14. Of course 7 goes into 14, but 4 does not, and 2 does. So these numbers are simple enough that just by looking at them and a little bit of thinking, you begin to realize that the number I want is 28. 14 will go into 28 twice. 7 goes into 28 4 times. 4 goes into 28 7 times. 2 goes into 28 14 times. So each of these numbers will divide into 28. And our claim is that it's the smallest number that each of these will divide into. Because for that matter, 56 is divisible by each of these, but it's larger than that. So usually we want the smallest because it will give us the least amount of work. In the kinds of fractions you have worked with in elementary school, you've dealt with denominators that generally are so small that you can just look at them and see that least common multiple of the denominators. We're about to move into a situation where we will be dealing with series of numbers where it is anything but obvious as to what is the lowest number that these 4 rather messy numbers will divide into. By the way, it's 296,352. And I doubt if anybody, at least nobody that I know, can look at these and just know it's going to be this number. So do you recall now, once and for all, the technique we taught in Chapter 2 and have been reviewing the last few lessons on finding the least common multiple as a series of 2 or more numbers? Let's use this example to once and for all nail that down, because as we go into the next lesson, we must assume that doing a problem like this is a very routine process for you. If it isn't, the next few lessons will be quite difficult. If it is a routine, the next few lessons will be quite simple. If your progress has been proper up to now, you should have a series of rules memorized on how to find that least common multiple of a series of numbers. If you somehow have snuck past the last chapter and last review lessons without having this procedure memorized, it's very important that you not go on with future lessons until it has been. So let's see if you do. What would be the first thing you would do to that series of numbers that we wish to find the least common multiple of? First, you're going to prime factor each number and write in exponent form. What next? You're going to write down each different base for factors to be. What next? You're going to give to each base its highest exponent. What next? Nothing. You're done. Just 3 very simple steps. Simple to remember, although we all agree it will take a considerable amount of arithmetic to do each one of these. So let's go through and follow through on each of these three regarding these. First, we want to prime factor each number and write in exponent form. Using some scratch paper here, let's prime factor together, let's say the messiest one here, just to remind ourselves how it's done. Then, to save us time on the videotape here, I will just give you the results of the other three. So to prime factor a number, we find the lowest prime number, which in this case is 2, that will divide this. And in this case, let's use a calculator, speed ourselves up. 378 divided by 2 was 189. 2 will not divide into that anymore, so we go to the next prime number, which is 3. And we see if 189 is divisible by 3, and that was 63. And of course we had a divisibility test which said to add up the digits, so 1 and 8 and 9 is 18. So since 3 divides into the sum of the digits 18, it must divide into the whole number. Same thing here, even without a calculator, we can see that 3 divides into 63. And again, 3 divides into that quotient of 21 7 times. So now we know that 378 is 7 times 3 times 3 times 3 times 2. And each of these are prime numbers. Do recall it's very important that they be prime numbers. After all, we are prime factoring. So now our step was to prime factor. We have done that. And write in exponent form. So we have 1 2 factor, so it's 2 to the first, 3 factors of 3, so 3 to the third power, or 3 cubed, and 1 factor of 7. So we have prime factored 378 and written it in exponent form. It's very important that you realize that this is simply another way of saying this number. Now, doing the same kind of procedures exactly, we want to prime factor the remaining numbers in our series. And if we did that, we would find the prime factorization of 343 would be simply 7 to the third power, or 7 cubed. So this is simply another way of saying that. Now, doing the same procedure to this, we would find that it prime factors to 2 to the fifth power times 7 to the first power. So this is simply another way of saying 224. Then 98 is so simple we can almost prime factor that mentally. We can see that 2 goes into 98 49 times, and 49 is 7 times 7. So here we have the prime factorizations of each number in our series. Please note the procedure was simple enough. It's simply repeated divisions. So when we said that we want this to be simple to you, we meant just that. But being simple sometimes is quite different than taking a lot of time. And there's a lot of time involved with this, but that's just the nature of the game at this stage. So in finding the least common multiple of these three, we have reviewed the first rule of prime factoring each number and writing it in exponent form. The next rule was write down each different base for factors to be of our least common multiple. So I see I'm going to need a base 2. I will need a base of 3 if I want to put them in sequential order. And I will need a base 7. There is no other base used anywhere other than 2, 3, and 7. So our second step is quite simple and has been done. Then our third step is to give to each base its highest exponent. So the exponent on 2 is 1 there, 5 there, 1 there, so the highest exponent was 5. The highest exponent on 3, there's none there, none there, none there, but 3 here. And the highest exponent on 7, 1 there, 1 there, 2 there, but 3 here. And these were factors to be, so we have given to each base its highest exponent. Then our claim is, we're done. That is this number. And here is written in, of course, prime factored exponent form. But that number is the least common multiple. That is, whatever this number is in standard form, it's the lowest number that each of these would have divided into. So let's see what this is. This is 5 2's being multiplied. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. This number is 3 3's being multiplied, so 3 times 3 is 9, times 3 is 27. This is 3 7's being multiplied, so 7 times 7 is 49, times 7, either by hand or by calculator. So 49 times 7 is 343. So completing our multiplications, and let's do it on a calculator, we have the 343 times 27 times 32 equals 296,352. And of course, just a moment ago, that was our claim. A lot of arithmetic, yes. Time-consuming, yes indeed. But difficult? Not at all, if you have these 3 very simple procedures memorized. So, use that procedure if necessary, but always, if you have a series of numbers and they're fairly simple, trust your own intuitions first and simply look at them and ask, what's the lowest number that each of these would have divided into? And usually, you will see it without using these procedures. So these are procedures you use when the numbers are so messy you just can't see what that least common multiple is. In the next lesson and a few following that, you'll see why this is so very, very important. But since we have a few moments left in this lesson and this review, let's take a peek ahead. Here we have 2 fractions, and if we were to focus on the denominators alone and to ask what's the least common multiple of those 2 numbers, of course it was 24. But also recall from our fraction building lesson that I can change the form of this fraction so it certainly looks different, but really isn't. And the procedure we used was to multiply top and bottom by the same number. Choosing 2 here, I would have got 6 16ths. And this certainly looks different from that, but really isn't. I could have also chosen to multiply top and bottom by any number. Let's say 7, and I would get 2156. And this really looks different from this, but in value it really isn't. And the point we made was that you can multiply top and bottom by anything you wish, and the value of the original fraction does not change even though its appearances do. So in particular, here I could have multiplied the top and bottom of this one by 3, and the fraction would be assume the form 9/24. But here is another fraction, And I could just as well have multiplied its top and bottom by anything I wish, different from this if I wish. So had I chosen 4, this fraction assumes the form of 4 24ths. So now we have two fractions which indeed have the same denominators, even though they started not having the same denominator. Now, can you begin to see the pattern of what we're going to do in the next chapter, the next lesson, when we wish to add fractions that don't have common denominators? We're simply going to make them have common denominators by using that least common multiple. So that means if one cannot find the least common multiple, this kind of a problem simply is not going to be possible. But if one can, it's a fairly routine procedure. In the meantime, let's return in our last few minutes to the main problem of this lesson, and that is to add fractions whose denominators are the same. It's as though being the same gives us permission to add. And of course, if we're adding fractions, we really have two questions concerning whole numbers. How do I get the bottom of the sum fraction, which is a whole number? Then how do I find the top, or the numerator, of the sum fraction, which is a whole number? And to find the denominator of the answer is very simple. It's the same as these like denominators, so we do nothing there. Remember, that's quite a bit different than multiplying and dividing, wasn't it? There we had to work with both top and bottom. But when we're adding, and it will be the same for subtracting, if the bottoms are the same, you have permission to add, and the bottom stays the same. Then to find the top or numerator, you simply add these tops. So that's 12. That's 12, and 12 and 12 is 24. And then, of course, always, without even being told, check your fractions, your answer part of your fraction, to see if it can be reduced. And we can see that 12 goes into here twice, and 12 goes into here 3, and this is the reduced sum of those 4 fractions. Simple? We hope so. We want it to be. Another one. As soon as we see the addition or subtraction, you immediately look to the denominators and ask, are they the same? If they are, then that is the denominator of my sum. Then immediately you look to the numerators and simply add them. And again, recalling from our chapter on whole numbers that you need not add from here to here to here to here. Frequently, it's more convenient to skip around to find easier combinations, combinations you can do mentally. So here you see that you have 20, so just hold that in your mind. You've got a 20. Now here you have 26. So 26 and 20 you can do in your mind and get 46. So frequently, by using the laws we taught in chapters 1, the commutative and associative laws, which permit you to add in different orders, you can make what would have to be a paper and pencil task into a mental task. Then reducing, we can see that 2 goes into here 23, and 2 goes into here 19 times. So here we have our reduced sum. Frequently, you want this changed into a mixed number. So we can see mentally here that 19 goes into 23 once, and that will leave a remainder of 4 out of 19. Please make a note that going from here to here is not called reducing. This is changing an improper fraction to a mixed number. Reducing simply meant I have divided top and bottom by all possible divisors, common divisors. Frequently in algebra, this improper fraction is the preferred form and you quit here. Frequently in business math situations, you need the mixed number. So it's not a matter of which one is right, they're both right. The real question is, once you have a sum, which form, the improper reduced fraction or the mixed number reduced fraction, which of those two forms does the user of this problem want? They're both correct, they're both good. Which one you have is purely a matter of preference. And if the numerators and denominators get larger or messier, it really doesn't make the problem harder, just involves a little bit more time of doing the same thing. The first thing you look at when you have an addition or subtraction of fractions is the question, are the denominators the same? If they are, then that becomes the denominator of the answer. Just that simple. Then you simply add, or as it will turn out, subtract, if that's the case, the numerators. And if it gets messy, you simply use paper and pencil and be careful, or you use a calculator. So 129 plus 235 is 364. And of course, whether you use a calculator or whether you do it by hand really depends upon what kind of skills your teacher is trying to work with you on at that moment. So if you're still weak at doing long whole number arithmetic, your teacher will be very wise to not allow this for a while and insist that you do this with paper and pencil. But if, on the other hand, you are good at this, then it might be desirable to allow you to gain speed by using a calculator. And if you are allowed to use a calculator, then also use it to reduce. See, we can see by looking at these two that they're each divisible by 2. So we have the top already on the calculator. So let's divide it by 2 while we're there. And we get 182. Then divide the bottom, 578 by 2, and we get 289. Now we know 2 will go into the top still, but not to the bottom. So it might still be reducible by other prime divisors, 3 or 7 or 11 possibly. And if you were to try the other possibilities, you would find that indeed this is already reduced. But again, the core of this lesson is in order to add fractions, the denominators must be the same, they stay the same, you add the tops, then reduce and or change to mixed numbers. This should be an easy lesson. Enjoy it. This is your host, Bob Fennell. We'll see you at the next lesson.